Inference and induction. At a fundamental level, when we think about thinking, we are often considering cognitive actions like figuring out a problem, or trying to predict how someone will react, or relying on our knowledge and existing conceptual representations to make sense of and interpret new events. Another way of describing this behavior is that we rely on our past experiences to predict what might happen in the future in similar circumstances. In previous chapters, I have given the example of shopping at a farmer's market, so let's consider that example again. When I go to the farmer's market, I rely on my past experiences to help me predict what to expect the next time I go. I expect there to be vendors, produce, and other shoppers, and prepared food. If I pick up a butternut squash, I can predict what it will look like on the inside based on my prior knowledge of similar butternut squashes that I have purchased and processed in the past. The entire experience is one that relies heavily on prior knowledge to make predictions. The entire experience is one that is made predictable and manageable on the basis of prior knowledge. The inductions and predictions all seem straightforward, and the process happens so quickly that we do not realize the power inherent in what we are doing. We are using the past to make predictions about the future, and usually these predictions come true so often that we don't even notice. And when our predictions don't come true, we often ignore or downplay evidence to the contrary. This is the power of inductive reasoning. Induction is about predicting the future. Objectives. On completing this chapter, you should be able to achieve the following: understand the basic definitions of induction, inference, and generalization. Be able to explain why some philosophers and psychologists believed that induction is a problem and why it is difficult to explain. Be familiar with the basic phenomena of inductive reasoning, how people behave in experimental settings, and with logical fallacies related to inductive reasoning. Understand and explain the two primary theories of inductive reasoning: similarity coverage and feature coverage. The role of induction in thinking. Inferences and conclusions. Induction or inductive reasoning is a process that we use for many common activities and behaviors. For one, we use induction to make inferences. Inferences are conclusions based on the available or observable evidence. These conclusions might be used to make a prediction about a specific event. For example, I used to get telephone calls from telemarketers between the hours of 4 p.m. and 7 p.m. I don't get these calls as much anymore, primarily because I no longer have an old-fashioned landline telephone. Those hours between 4 p.m. and 7 p.m. would be a time when many but not all people are home from work or school, making and or eating supper. When the phone would ring at that time, I usually made an inference or prediction that the caller was just trying to sell something, so I rarely picked up the call. Because this had happened in the past, I made enough observations to draw a reasonable conclusion about who would be on the phone. On the other side, the telemarketing company was relying on their evidence to make an inductive inference that I would be at my home phone between 4 p.m. and 7 p.m. We were both making inductive inferences. Generalization. Induction is also used when we make generalizations. A generalization is also an inductive conclusion, but rather than describing a specific prediction, as in the previous examples, generalization is a broad conclusion about a whole class or group of things. These generalizations inform the conclusions we make, and these conclusions affect our behavior. If you see the sun rise every day, this will lead to a generalization that the sun always rises, and that generalization allows you to predict something about the sunrise tomorrow and the next day. If you enjoy a really good espresso at a particular cafe several times in a row, you will probably begin to form a generalization about that cafe, and that will affect your expectations. On the other hand, if you had a bad dinner at a restaurant, you might form a general impression of its poor quality, and that would affect your predictions about future meals and would reduce the likelihood that you would want to eat there. You are using your past experience to generate a mental representation, the generalization, that you will use to guide your behavior. We also form generalizations about people based on our experience with one or more individuals. For example, Let's consider the thinking behind football rivalries. In the UK, there are many fierce rivalries between football clubs in the Premier League. Some of the rivalries are based on history of play, and others are rivalries based on fan experience. Imagine a person who supports Arsenal FC and suppose that they have had less than positive experiences with some Chelsea FC fans, or the other way around. I'm not picking sides. Based on a few of these negative interactions, the Arsenal fan might form a negative generalization about Chelsea fans. That generalization may be based on limited evidence or even indirect evidence. This is the basis of many stereotypes and prejudices. One of the reasons that stereotypes are so difficult to overcome is that they arise from the basic cognitive processes that underlie all generalizations and inferences. In the examples above, whether or not the conclusion was made about a specific telemarketing call or a general conclusion about Arsenal or Chelsea fans, the evidence was specific. Inductive reasoning involves making specific observations and then drawing conclusions from that available evidence. It seems that we make inferences all the time. If you call a restaurant to place an order for a pickup delivery takeaway, you make a basic inference that the food you order will be ready for you to collect. When the driver in front of you puts on his turn signal, you make an inference that he will turn left or right. We rely on induction to make inferences about how people will behave and react to what we say. We rely on induction to make inferences about how to use new ingredients when cooking dinner. Young children rely on induction when they pick up an object and learn about how size predicts the weight of objects. Parents make inductions when they predict how their young children might behave after a short nap or a long nap. The list is extensive because induction is such a critical aspect to the psychology of thinking. In summary, we rely on inductive reasoning to discover something new by thinking. How induction works. Induction is central to our thinking, and as a result, philosophers and psychologists have been thinking about and studying induction for centuries. Let's look at the history of induction as an area of study. This history is fascinating because it's full of paradoxes and quandaries, and many of these ideas are still relevant today. Hume's problem of induction. In the era of the Scottish Enlightenment, the philosopher David Hume considered induction to be one of the greatest problems for philosophers to solve. Unlike deductive logic, which I discuss in Chapter 7 and many contemporary philosophers believed could be explained by formal mathematical operations, induction seemed to defy this. Hume gave a description of what he called the problem of induction. As we discussed, induction is essentially the act of relying on past experience to make inferences and conclusions about the future. Hume was concerned that this was a circular argument. The reason was as follows. Induction works because we assume that the future will resemble the past in some way. We must have confidence in our judgments about the future. Hume claimed that this only worked because the future has always resembled the past in the past. To say that the future has always resembled the past in the past might strike you as unnecessarily confusing, but what this means is that your inductions and conclusions were probably correct in the past. You might be able to recall inductions and conclusions that you made yesterday, 2 weeks ago, or 2 months ago that turned out to be true. As a concrete example, if you were at a farmer's market yesterday and you made an inference about what the inside of a Hubbard squash would look like, and your prediction was later confirmed, you could say that yesterday, the future resembled the past. The problem with this, according to Hume, is that we cannot use these past inductive successes to predict future inductive successes. We simply cannot know if the future will resemble the past. In other words, it is impossible to know if your inductions will work in the future as well as they worked in the past without resorting to the circular argument of using induction. Just because your inductive inferences worked yesterday, 2 weeks ago, 2 months ago, does not guarantee that they will work now, tomorrow, or 2 weeks from now. Induction is based on the understanding that the future will resemble the past, but we only have information about how well this has worked in the past. To make this assumption requires the acceptance of a circular premise. In essence, we are relying on induction to explain induction. By now, your head might hurt from considering all the past futures and future pasts, and you would be right. Hume concluded that from a strictly formal standpoint, induction cannot work, but it does work. Humans do rely on induction. This is why Hume considered induction a problem. There is no way for it to work logically, and yet we do it all the time. We rely on induction because we need to. Hume suggested that the reason we rely on induction is that we have a habit of assuming that the future will resemble the past. In a modern context, we might not use the term habit, but instead would argue that our cognitive system is designed to track regularities in the world and make conclusions and predictions on the basis of those regularities. Let's consider some of the fundamental mechanisms that allow induction to work. Basic learning mechanisms. All cognitive systems, intelligent systems, and non-human animals rely on the fundamental processes of associative learning. There is nothing controversial about this claim. The basic process of classical conditioning provides a simple mechanism for how inductions might work. In classical conditioning, the organism learns an association between two stimuli that frequently co-occur. In Chapter 2 on similarity, we discussed the example of a cat that learns the association between the sound of the can of food opening and the subsequent presentation of her favorite food. The cat has learned that the sound of the can being opened always occurs right before the food. Although we tend to talk about it as a conditioned response, it is also fair to discuss this as a simple inductive inference. The cat doesn't have to consider whether or not it is reasonable that the future will resemble the past. She simply makes the inference and acts on the conditioned response. In other words, the cat makes a prediction and generates an expectation. Stimulus generalization. Another conceptual advantage of relating induction to basic learning theory is that we can also talk about the role of similarity and stimulus generalization. Consider a straightforward example of operant conditioning. Operant conditioning, somewhat different from classical conditioning, is characterized by the organism learning the connection between a stimulus and a response. We can imagine a rat in a Skinner box learning to press a lever in response to the presentation of a color. If a red light goes on and the rat presses the lever, it receives reinforcement in the form of rat food. If the blue light goes on and the rat presses the lever, it receives no reinforcement. Not surprisingly, the rat learns pretty quickly that it needs to press the lever only when the red light comes on. We can argue that the rat has learned to make inductive inferences about the presentation of food following various lights or even different colors. However, the rat can do more than just make a simple inference. The rat can also generalize. If you were to present this rat with a new color that was slightly different from the original color that it was trained on, it would probably still press the lever. Its rate of pressing might decrease, however. You would also find that the rate would decrease as a function of this similarity. The more similar the new color is to the training color, the higher the rate of lever pressing. Figure 6.1. This decrease is known as the generalization gradient. So pervasive is this generalization gradient that Roger Shepard referred to it as the universal law of stimulus generalization, 1987. Not only is the rat making what amounts to an inductive inference about the relationship between lights and food, it is also making these inductive generalizations in accordance with the similarity between the current state of affairs and the previously encountered instances. Figure 6.1, an example of a typical generalization gradient. The animal, a rat for example, will press the lever vigorously when it sees a specific color, the middle gray. The maximum lever press rate corresponds to the peak. The rat also presses the lever when colors that are similar to that color are presented, but the rate of lever pressing drops off considerably as a function of decreasing similarity. So you can see in the diagram there's a normal curve, and on the x-axis is color, and in the middle is a middle gray, on the left is a dark gray, and on the right is a light gray. So the mean of the normal curve corresponds to the middle gray color. And on the y-axis is lever press, so you can see levers are pressed the most for the middle gray color and colors that are similar to it on either side. The title is Generalization Gradient. What we see is that there is something fundamental and universal about generalizing to new stimuli as a function of how similar they are to previously experienced stimuli. This has implications for understanding induction. First, It strongly suggests that Hume was right. We do have a habit to behave as if the future will always resemble the past, and this tendency is seen in many organisms. Second, our tendency to base predictions about the future on similarity to past events should also obey this universal law of stimulus generalization. If one's past experiences are very similar to the present situation, then inferences have a high likelihood of being accurate. As the similarity between the present situation and past experiences decreases, we might expect these predictions to have a lower probability of being accurate. Goodman's problem of induction. Although stimulus association and generalization seem to explain how induction might work at the most basic level, there are still some conceptual problems with induction. According to Hume, induction may be a habit, but it is difficult to explain in logical terms without resorting to some kind of circular argument. Hume's concern was not so much with how induction worked, but rather that it seemed to be difficult to describe philosophically. Nelson Goodman, the 20th century, 1900s philosopher, raised a very similar concern, but the example is somewhat more compelling and possibly more difficult to resolve. 1983. Goodman's example is as follows. Imagine that you are an emerald examiner. I know this is not really a thing, but just pretend that it is. Every emerald you have seen so far has been green, so we can say that all emeralds are green. By ascribing to emeralds the property of green, what we are really saying is that all emeralds that have been seen are green, and all emeralds that have not yet been seen are also green. Thus, emeralds are green predicts that the very next emerald you will pick up will be green. This inductive inference is made with confidence because we have seen consistent evidence that it is true. Figure 6.2. This is a schematic of Nelson Goodman's example of the concepts of green and grue emeralds. As can be seen, all the emeralds set up and seen so far are simultaneously green and grue, and so both properties are true. Emeralds that have not yet been seen are to the right of the black line. Each property makes a different prediction about the subsequent emeralds to be examined. Okay, so you can see there's a black vertical line, and on the left it says all the emeralds that have so far been seen, so they're all green and they're all grue. And then to the right of the line there's emeralds to be seen, and what are they going to be like? Are we going to assume green and grue? Called an example of green and grue. But there is a problem with this. Consider an alternative property called grue. If you say that all emeralds are grue, it means that all the emeralds you have seen so far are green, and all the emeralds that have not yet been seen are blue. Green emeralds in the past, but blue emeralds from this moment forward. Yes, this sounds a little ridiculous, but Goodman's paradox is that at any given time, this property of grue is true. Both properties are true given the evidence of green emeralds. Okay, that's why in the diagram you can see that the emeralds to be seen, the grue ones, they're a darker color than the green ones. I've illustrated this in figure 6.2. Notice that the past experience, green emeralds, is identical for both properties. Goodman's suggestion is that both of these properties, green and grue, can be simultaneously true given the available evidence. It is possible that all the emeralds are green, and it is also possible that all emeralds are grue, and that you've seen green-colored ones, but not the blue-colored ones yet. But these properties also make opposite predictions about what color the next emerald you pick up will be. If green is true, then the next emerald will be green. If grue is true, then the next emerald will be blue. And since both are true, a clear prediction cannot really be made, and yet, of course, we all predict that the next emerald will be green. Why? This is the problem of induction. Viewed in this way, induction is a problem because the available evidence can support many different and contradictory conclusions. Entrenchment and natural kinds. With the earlier problem of induction defined by David Hume, the solution was straightforward. Hume stated that we have a habit of making inductions, and our current understanding of learning theory suggests that we naturally generalize. Goodman's problem of induction is more subtle because it assumes we do have this habit. If we have a habit to make inductions, how do we choose which one of the two possible inductions to make in the emerald example? A possible solution is that some ideas, descriptors, and concepts are entrenched and thus more likely to be the source of our inductions. Entrenchment means that a term or a property has a history of usage within a culture or language. As we have discussed earlier in Chapter 5, there is still considerable evidence that language can influence and direct our thinking. In the emerald example, green is an entrenched term. Green is a term that we can use to describe many things. It is a basic color term in English. It has a history of usage within our language, of being used to describe many different categories of things, and so it is the useful property to make predictions from and about. By saying that a collection of things, emeralds, is green, we can describe all the things. Grue, on the other hand, is not entrenched. There is no history of usage and no general property of grue outside the emeralds that were grue yesterday and blue tomorrow. Unlike green, grue is not a basic color term and does not apply to whole categories. Goodman argued that we can only make reliable inductions from entrenched terms and from coherent categories and from natural kinds. The philosopher W.V.O. Quine, in his essay Natural Kinds, 1969, argued that natural kinds are natural groupings of entities that possess similar properties, much like what we have referred to earlier in Chapter 4 as a family resemblance concept. Quine suggested that objects form a kind only if they have properties that can be projected to all the members. For example, an apple is a natural kind. This is a natural grouping, and what we know about apples can be projected to other apples. Not apple is not a natural kind because the category is simply too broad to be projectable. This grouping consists of everything in the universe that is not an apple. Quine argued that all humans make use of natural kinds. Reliable inductions come from natural kinds. Granny Smith apples and Gala apples are pretty similar to each other and belong to the same natural kind concept. Anything you know about Granny Smith apples can be projected to Gala apples with some confidence, and vice versa. The same would not be true of Gala apples and a red ball. True, they may be similar to each other on the surface, but they do not form a natural kind. Whatever you learn about the Gala apple can't be projected to the red ball. Quine's notion of a natural kind suggests a solution for Nelson Goodman's problem of induction. Quine pointed out that green is a natural property and that green emeralds are a natural kind. Because of this, the property of green can be projected to all possible emeralds. Grue, being arbitrary in nature, is not a natural kind and cannot be extended to all possible members. In other words, green emeralds form a kind via similarity. Grue emeralds do not. Green emeralds are a coherent category, whereas grue emeralds are not. Green and grue might both be technically true, but only one of them is a coherent category and natural kind, and a group with a consistent perceptual feature. And so we are able to make inductions about green emeralds and do not consider making inductions about grue emeralds. Categorical induction. If we consider the research discussed above, we can first conclude that most organisms have a tendency to display stimulus generalization. This can be as simple as basic conditioning or generalizing about a group of people. Second, basic stimulus generalization is sensitive to the similarity between the current stimulus and mental representations of previously experienced stimulus. Third, we have shown in other chapters that concepts and categories are often held together by similarity. As a result, a productive way to investigate inductive reasoning is to consider that inductions are often based on concepts and categories. This is known in the literature as categorical induction. By assuming that induction is categorical, we make an assumption that there is a systematic way in which the past influences future behavior. The past influences the present and judgments about the future as a function of conceptual structure. The structure of an induction task. For the present purposes, we can define categorical induction as the process by which people arrive at a conclusion or a statement of confidence about whether a conclusion category has some feature or predicate after being told that one or more premise categories possess that feature or predicate. This is just like our ongoing example about winter squashes. If you learn that a winter squash has fibers and large seeds inside, and then learn that the Hubbard squash is also a winter squash, you use your knowledge about the category of winter squash and the features that are typical of that category to make the inductive inference. In this way, the conceptual structure of past knowledge influences your prediction that the Hubbard squash will also have seeds. In many of the examples I discussed below, the induction is made in the form of an argument. The argument is a statement which contains one or more premises that support a conclusion. A premise is a statement of fact about something, someone, or a whole class. The premise contains predicates, which can be things, and properties. In most of the examples, the predicates are properties or features that are common to the category members. The inductive argument also contains a conclusion statement. The conclusion is the actual inductive inference, and it usually concerns the possible projection of a predicate to some conclusion, object, or category. In an inductive argument, participants would be asked to decide whether or not they agreed with the conclusion. They might be asked to consider two arguments and decide which of the two is stronger. For example, consider the inductive argument below, which first appeared in work by Sloman and Legnato, 2005. Argument. Premise. Boys use GABA as a neurotransmitter. Conclusion. Therefore, girls use GABA as a neurotransmitter. The first statement about boys using GABA as a neurotransmitter is a premise. Boys are a category, and the phrase use GABA as a neurotransmitter is a predicate. How strongly do you feel about this conclusion? Part of how you assess the strength has to do with whether or not you think girls are sufficiently similar to boys. In this instance, you would probably agree that they are pretty similar with respect to neurobiology, and therefore you would endorse the conclusion. When you were answering this question, you may wonder what GABA is beyond being a neurotransmitter. You may not have actually known what it is at all, and may not have known whether or not it is present in boys and girls. So the actual answer to this conclusion is probably unknown. The statement is designed this way for a reason, though. The categorical induction statement works because it asks you to infer a property based on category similarity, rather than on retrieving the property from your semantic memory. Thus, in the example above, GABA is a blank predicate. It is a predicate because it is the property we wish to project, but it is blank because we do not assume to know the answer. It is plausible, but not immediately known. And because you cannot rely on your factual knowledge about GABA as a neurotransmitter, you will have to make an inductive inference on the basis of your knowledge about the categories, boys and girls in this case. Thus, the blank predicate is crucial in inductive inference research because it forces the participant to rely on categorical knowledge and induction rather than on the retrieval of a fact from semantic memory. Research using this paradigm has described several strong phenomena regarding how people make categorical inductions. These include inductions and conclusions about specific cases, and inductions and conclusions about whole categories. In most cases, the strength of the argument is dependent upon how similar the premise or premises is or are to the conclusion, and categorical structure plays a role as well. When we have evidence that a feature is associated with a member of a category that is highly typical, we tend to trust other inductions as well. Using this basic paradigm, we can investigate some general phenomena about categorical induction. Let's look at a few of these. Keep in mind that these phenomena tell us about how induction works, and by extension how concepts, categories, and similarity influence thinking and behavior. Premise similarity. For example, if the facts and features in the premise and the conclusion are similar to each other, are from similar categories, or are from the same category, inductive inferences can be made confidently. This is referred to as premise-conclusion similarity. According to Osherson et al., 1990, arguments are strong to the extent that the categories in the premises are similar to the categories in the conclusion. We are more likely to make inductive inferences between similar premise and conclusion categories. For example, consider the following two arguments. Argument 1, premise, Robins have a high concentration of potassium in their bones. Conclusion: sparrows have a high concentration of potassium in their bones. Argument 2. Premise: ostriches have a high concentration of potassium in their bones. Conclusion: sparrows have a high concentration of potassium in their bones. In this example, the high concentration of potassium in their bones is the blank predicate. This is the new property we are making an inductive inference about. Argument 1 should seem stronger, and in empirical studies, research participants found this to be a stronger argument. The reason is that robins and sparrows are fairly similar to each other. Ostriches and sparrows are not very similar. The low similarity between the ostrich and the sparrow is evident on the surface, as is the high similarity between the robin and the sparrow. We assume that if the robin and the sparrow share observable features, they may also share non-observable features, like the concentration of potassium in the bones. Premise typicality. The example above emphasized the role of similarity between the premise and the conclusion, but in the strong similarity case, you may have also noticed that the robin is a very typical category exemplar. For all intents and purposes, the robin is one of the most typical of all birds. And remember that typical exemplars share many features with other category members. Typical category members have a strong family resemblance with other category members, and they can also be said to cover a wide area of the category space. What is true about robins is true of many exemplars in the bird category. Premise typicality can affect inductions about the whole category. For example, consider the following set of arguments. Argument 1. Premise: robins have a high concentration of potassium in their bones. Conclusion: all birds have a high concentration of potassium in their bones. Argument 2. Premise: penguins have a high concentration of potassium in their bones. Conclusion: all birds have a high concentration of potassium in their bones. In this case, you might agree that the first argument seems stronger. It is easier to draw a conclusion about all birds when you are reasoning from a typical bird like a robin, which covers much of the bird category, than from a very atypical bird like a penguin, which does not cover very much of this category. If we know that a penguin is not very typical, it possesses many unique features, and does not cover very much of the bird category, we are not likely to project additional penguin features onto the rest of the category. We know that many penguin features do not transfer to the rest of the category.